This is starting at chapter 12, rated 12.1 today, temperature and thermal energy. We'll learn about the difference between heat energy and temperature, and we'll also talk about how heat is transferred. So thermal energy is the total kinetic energy a molecule has, or even a mass if you take all of the molecules in there, and add up the kinetic energy, the amount that they're moving. So heat is just the movement of atoms on a molecular level, on a really tiny level. They're moving. Right. So think about ice, right? Think about ice. It's stuck in a crystal structure. It's stuck like this, and it has some heat, so it's vibrating a little bit. And as you add more heat, it breaks those bonds with each other. They loosen up a little bit, and they expand. And so now it's water. It has more energy. It's moving more and more. And then you give it even more energy, and they start to break their bonds. So now they're free from each other, and they're just air molecules. They're vibrating around. They have a lot of energy now. They're free. So the atoms in the air here, right now, have so much energy that they are not bonding to each other. If we were to cool it down enough, you would turn into a liquid. And cool it down even more, take energy out of it, we turn into a solid. So that is what heat is. It is just how much your atoms are moving on an atomic level. Okay, that was thermal energy, the total energy. This is temperature, which is the average kinetic energy. So if you take, a small piece of air, this area here, some of the molecules will only be moving a little bit, and some of them will be moving a lot. So we take the average of that movement, and we call it average kinetic energy, which is our temperature. So it can vary widely, but if you look at it as an average, you will get the temperature. Now, hot objects have a higher average kinetic energy than cold objects, so those objects are moving around a lot more. Now imagine you had a couple of wooden blocks of different sizes. If they're sitting here in the room, they'd be 66 degrees. Well, 64 degrees. I don't know. It's cold in here.
Are you kidding me?
Yeah. So, well, let's check. 66 degrees in here.
It's not.
So, if you have two blocks, different sizes, they're sitting here at 66 degrees. They have the same average kinetic energy. If you take their molecules, take an average measurement of their movement across the whole block, it would be about 66 degrees. Now, that's temperature. So thermal energy is the total amount of energy. Since the bigger block has more molecules, it's going to have more energy because those molecules are all moving. And they're moving with the same, rate-ish as the smaller block, but it has more molecules, so it has more heat, more total energy. So temperature, average, heat is a total. And the more mass you have, the more energy you're going to have. Now this is the best part of physics. Best part of all of physics. In this whole year. This is the best part. So you need your hands out. Put your hands out. You gotta play along with me. Okay? Energy transfer. The first one is conduction. So touch it like it's hot. Conduction. Touch. Touch. Right? That's conduction. And the next one, circular motions with your hands. Hot rises, cold falls. This is convection. Convection happens in all fluids. Convection happens in all fluids. It happens in the ocean. It happens in the atmosphere. It happens in the sun, where there's plasma. And the last one, which is my favorite, is radiation. The sun gives off radiation, right? And so that light wave travels down through the sun to the earth, through space, right? Space is really cold. You think it would, interact, but it doesn't have anything to interact with. So it travels through radiation until it hits the earth, and then it releases its lovely heat energy, which keeps us warm. Not in this room, but everywhere else. So radiation. Radiation's like this. And if you go backwards, you get a squid.
This is how radiation travels, guys. Like a jellyfish.
Well, it does kind of look like a wave. Radiation is a wave. Well, it's wave-like. Okay, so we got those three. That's the best part of all physics.
If only the E-beam could take videos.
Maybe you just have a lower body temperature. You exist at like 75.
God, why are you?
Like a 103.
Oh, give me a hand. No, Carlos hands are normal temperature. Feel this kitten.
Yeah, I know.
I don't have to tell him this. Make it sound cool.
My mom's like that. She always has warm hands.
I'm cool.
No, I'm so
I'm normal.
Miss Phyllis, my country's having a famine. Can you solve that?
I don't resolve problems outside of the classroom. I'm sorry.
What if I move my country into your classroom?
I don't think it'll fit.
It's a pretty small country.
What?
All right, I still see a red cup. You guys using that there? Okay. All right, thermometry. So if you stick a cold thermometer in your mouth, the hot, warm molecules of your spit are going to bump into, right, because they're moving a lot, they're going to bump into the thermometer and make those molecules move more. So they're going to warm the thermometer up. Now they're going to lose a little bit of energy in doing that because now they're transferring their momentum to the molecules in the thermometer. So when you stick a thermometer in your mouth, not only does it warm up, but it also cools your mouth a little bit. So the act of measuring it here changes what your, what the original temperature was. No, it's cold. Well, I mean, originally yes. So if someone likes to take our temperature, how can you make it higher? Like like your sip. Oh, how can you make it higher? I don't know. Hot sauce?
Yes.
Doesn't that make you warm?
A hot pocket.
Like a hot pocket.
Yeah.
Just eat one of those and take your temperature.
I mean, yes, it does that too, but like you see people with face turn red. So I can see that happening. I'm gonna get you drink some hot tea. Are you taking notes on this? And drink some hot chocolate. Thermometers are accurate, but when you put the thermometer in your mouth, it cools down your mouth a little bit.
So we should put it in a lamp.
Yes.
Yes. Actually, they don't work.
It's, spit has a high specific heat and metal has a very low specific heat, so the amount that it's changing is very small. Not like a degree, like not even a tenth of a degree.
What about glass?
Why would you put one in your mouth?
They're still around the same as metal, because I think they're 600 or 700, and it's even water is 4,000. So the difference in them is very small.
Way to go, water.
But you can actually calculate it when I give you the equation.
You don't change water.
That's how we think our temperature is.
Just remember, the E-beam is recording everything you say, so the people that go back and try to listen to this will not be able to hear. That'll be for you, Andrew. I'm gonna break your chair. All right. So this occurrence of the thermometer changing the temperature, right? It's changing the temperature of your mouth, and the thermometer itself is changing temperature. These two things are coming to thermal equilibrium. They're both becoming the same temperature. They're trading their kinetic energies. This hotter object is speeding up the colder object so that they become the same temperature. So hot always moves to cold. The energy is transferred. Now this one loses some energy and this one gains some energy. But there is no cold molecule. It's just energy. Heat is only energy. So you're not really letting the cold out. You're letting the heat in.
I'm going to let the heat in.
And we're going to learn how to calculate thermal equilibrium today. You've probably seen it in your chemistry before. So it should be pretty easy. I have the equation. I also have a grid.
Oh, yes.
But you don't have to use the grid if you don't want to, because it's a pretty easy equation. It's like the momentum stuff.
So the hot object never gains cold, but it lowers
It
the
loses
temperature.
energy. Yeah, think of it as energy and not as hot. It's not like a hot molecule. It's moving along, and it runs into things that are slow, so that it slows down and the other thing moves more, so that the high rate. This is probably.
When you want to go like 100 miles an hour? Yeah. Dumpster truck.
Lewis. Don't say swam.
It's like they're of one mind.
Okay, there are 3 different temperature scales: Fahrenheit, Celsius, and Kelvin. Fahrenheit is what we use here in the U.S., but it's kind of dumb. 32 degrees is freezing for water, and 212 is boiling for water, which is really strange. So they came up with a different one. Some guy with the last name Celsius, I can't remember his name, but I'm pretty sure.
Celsius.
Who?
Celsius.
Sure, we can call him that. He set the freezing point of water at 0 degrees and boiling at 100. So this is what they use all over the rest of the world.
Like normal people?
Like normal.
Well, yeah.
So I would learn how to do this if I were you.
Countries that went to the moon use Fahrenheit.
Oh.
Yeah.
Countries that didn't go to the moon use Celsius.
Yeah. Okay. And then we have this other one, Kelvin, who this one was definitely named after a guy, Lord Kelvin.
Lord Kelvin. Oh, hell.
All right, I can't remember his name, but I know he was a lord.
Lord Kelvin, that's all we need.
All right. What he did is he took the Celsius scale, and so it still goes 1 degree change in Kelvin is all change in Celsius, which is important for our equations. But he took the 0 and dropped it all the way down until the molecule is not moving at all.
Which is impossible.
it is not impossible. It used to be we thought it was impossible because space is about 2 degrees Kelvin. But they were actually able to slow a molecule all the way down to 0 and even into the negative temperatures. And this was about a year ago. There's a paper on it. If you search negative temperatures in Google, and the articles will pop up. But they actually did negative temperatures, and it started to move around a lot, and it was very, very hot.
I told you, man. Negative
So
temperature.
the temperature scale
Who called
is
it?
cyclical.
Who called it?
Well, you
This
don't
guy.
have to believe it.
Wait,
So negative temperatures are hotter than the sun, according to the paper that I read, which is interesting.
Which is false also.
Negative Kelvin temperatures. Just like 0 is not moving. And so negative temperatures are like super. So it's so cold that it's burning. Okay.
That's what I think, but I'm like, is that really making sense?
Okay, so you should have these 2 equations down. You're going to need them. For most of our stuff, it'll either be in Celsius or Kelvin. If you're not sure what to put it in Kelvin, because Kelvin will work every time.
Kelvin's the best.
just reopen and just keep it recording. Just like
Okay, so why is everything not the same temperature? How come I'm 98 degrees and it's 66 degrees in here?
Because I said
It's just the way.
It could be the fact that I'm wearing 3 sweaters.
Yes.
But it's insulation. It is specific heat. The specific heat of the air here is very, very low. It doesn't take much energy to change that temperature. But the specific heat of my fat, which I do have somewhere, is a lot higher. It holds on to that heat. It has a large specific heat. Water has the highest specific heat. Well, I don't know if it's the highest, but it's very high. It's 4,000. Right? I think in chemistry you guys learned it as like 4. Here we talk about it as 4,000 because of the units that we use are a little different. We use SI units instead of CPS. So this is an equation. It is a little bit different than what it's up here. I'm going to show you 2 versions of it. One of them is total energy. So this is the total energy of what you're looking at, and it is MCT, where this is in Kelvin. This one, it doesn't ask for very often, but it'll say something about the total energy. And then sometimes it'll say how much energy is required to raise it this much temperature. And that's a change in energy. You're adding energy to the object. That's MCAT. And this one can be in Kelvin or Celsius. So if you see a change in temperature, because the change in Kelvin is the same as the change in Celsius, you can use either one. But if it's a total, you have to use Kelvin, because this Kelvin is based on the absolute 0 scale. If you're not sure what to use Kelvin.
Okay, so I have a question. T in this equation is temperature.
Yes.
C.
It's a specific heat, which is that paper that I gave you.
What's Q?
Q is the energy.
Energy.
Yes.
Water is unusually high. Why would it have such a high specific heat?
It has a high specific heat because it requires a lot of energy to heat it up.
Because the particles are like so far apart.
I'm not really sure, like, what about the particles makes them change. There is probably electron configuration, the fact that water's polar, and some other things that go into actually the reason why that it has such a high specific heat. Yeah. But like water is 4,000 and steam is only like 2,000. And ice is only like 2,000. But water itself, which is why I think it's something to do with the fact that it's polar, is 4,000, which is double those things. But if you look at the little piece of paper I gave you, it says specific heat. You can see all the different specific heats on there, which is actually on the next slide. If you guys are ready.
Lead. That was gross.
Okay, you can do whatever you want.
Okay, so this is a table that's on page 318. I also gave you a copy of it on that piece of paper. And if you look on the back, there's expansion stuff 2, which we'll talk about in chapter 13. So if you take a look at it, notice a lot of the metals are fairly low. And then you get ice, it's like 2,000, and steam is 2,000, and then water is like 4,000. So water requires a lot of energy to get it to change its temperature. It's actually a very good insulator, which is why Earth seems to remain a very constant temperature. If you look at the east coast side of the United States, they get the nor'easter snowstorms and stuff. And the temperatures range, they have hot summers and cold winters. If you go to the Pacific Northwest, where I'm from, our temperatures really don't range very much. The lowest it usually gets is like 15, and the highest it gets is like maybe 90, like once or twice a year. 15 degrees. Which is weird to, think about as Florida, but we're surrounded by water. We're on a peninsula, so there's water all the way around us, and there's a lot of water in the air. So we remain a very constant temperature. But the Pacific Northwest remains an even more constant temperature. Anything around the Pacific doesn't really change too much because it's a very large body of water. Okay, yes?
That makes it feel cooler down here than
Definitely doesn't feel cooler.
I think that has to do a lot with the water in the air. Again, it's a good insulator, so the temperature isn't going to change very much. But if you go from here up north, there's a lot less water in the air, so you get colder quicker because it's not insulated. Okay, so calorimetry. This is the lab that you're going to do next week. We're going to put frozen marbles in warm water in this calorimeter. Now, the calorimeter is made of 2 cylinder cups. We have an outside and an inside, and there's air in between them so that it's insulated. So you put the warm water in, and you're going to measure its temperature, and then you're going to have these ice-cold marbles, which I'll tell you what the temperature is when I do it. And then, so you know both the initial temperatures. You put those cold marbles into the warm water, and then wait for the temperature to stop changing. So the cold marbles are going to warm up, and the warm water is going to cool. This is equilibrium. This is thermal equilibrium. Here's the equation for that. It just says the energy of the marbles and the energy of the water before you put them together is going to be the energy of the marbles in the water after, but they're going to have the same temperature. So they're going to trade energy until they get the same temperature. So you'll be able to calculate the specific heat of these marbles. And I'm going to write this on the board here because we're going to use it. Say it again?
Probably just, blew out the EV.
Nope, not. Actually, I might have crashed. Let's check. Nope, it's still working.
Darn.
All right, so this total, one object is asked for the total energy of that object at one temperature. This one, still one object, but it's changing temperature. There should be 2 temperatures in the equation. So this is like how much energy you add, how much energy you take away, something like that, some sort of change in energy. This one is going to have 2 objects, and you're going to put those 2 objects at 2 different temperatures together, and then they're going to have some final temperature. So 2 objects, 1 object, change in energy, total energy. And that should help you. I'm going to write the grid up here real quick so that you can see that this equation can also go in the grid. You don't have to use the grid, but some people get confused because there's so many variables. So here's the grid for you. It looks just like the momentum grid. And you're going to put MCPQ at the top. And you're going to have initial, final, object 1, object 2, object 1, and object 2. And then, just like we did with the momentum, you're going to multiply these together to equal Q. After you do that for each row, you'll add the first 2 and set it equal to the second 2. So initial will equal final. And then you can rewrite and solve.
It's that.